Hi, we're back with Mukul to talk about frozen objects in this episode of On .net. Hi friends, welcome to the next episode of the On .net show. I'm Maoni, the owner of the .net Core garbage collector.
Hey, I'm Mukul. I work on the Bing performance team.
So Mukul, last time we were going to talk about frozen objects, right? That's one of the features that you're using during your startup stage. So frozen objects had existed in CLR for a long time. I mean, I'm talking like it started to appear, I think, in CLR 2.0, not .NET Core, but .NET 2.0.
.NET 2.0.
Yeah. So why did we have this feature? Well, if you observe that some objects are immutable, right? They don't change after you create them, and very likely that they would live throughout the process lifetime. So it would be nice if we could save the work to have to reprocess them every time we say do a Gen 2 GC, right? Because if a large part of your Gen 2 consists of these immutable objects, we wanted to optimize that, right? So we introduced this feature called frozen objects. In the GC's perspective, they actually live on segments that we call read-only segments, right? So normal GC heap lives on read-write segments because you modify them. But read-only segments are for users to put their frozen objects on. And we use this on frozen strings. I think that's the only object type we actually use this on, right? So can you tell me what in your scenario that that made you want to use this feature?
Yeah. So we basically when I found out about frozen strings in CLR 2 days, obviously much later, and then I tried them in, I was like, oh, it'd be great to try them in the next versions of .NET Framework. I think it's been if-deffed out or has been disabled in the actual .NET frameworks after 2.0, but in .NET Core, we sort of were like, hey, we'd like to use it. And the use case for us is that we have these ini files. They're these large, call them in-memory database, read-only.
Right.
It's essentially like a configuration data, other sorts of things that we never change or will change either after a process is torn down. It's essentially read-only. And I was thinking it'd be great if we could actually have all these objects, which have to be read from this ini file as strings, parse them, do all this work at startup, essentially to make them never be able to change them. So I was thinking, wouldn't it be cool if we could use this? And these can get large, like multi-gigabytes.
Right, yeah. It would be nice if GC doesn't need to reprocess them.
Them,
The cost of read-only objects or read-only segments in GC is very little compared to read-write ones. Because all we do is, if we observe that they're in range means if they're in the GC heap range, right? We have a lowest and highest address for the GC heap. And then if a segment of read-only objects or frozen objects happens to land in this range, we have to basically materialize the GC bookkeeping for it, right? Because you might be using the mark bits on it and whatnot. And when GC actually happens, all we do is, we would naturally mark there, and then you just clear the mark bits. That's all we do. So it's very cheap compared. So, what you just described sounds like a perfect scenario for using the frozen objects. And of course, if you want to use this feature, you have to somehow construct these objects, right? They can't appear in thin air, so you have to construct it. And historically, we just constructed them in the runtime itself, right? The runtime would go make frozen strings, somehow construct them.
The engine.exe would compile them into
and then put them in the image, and then when the CLR is loaded, we'll load them up. Basically, all they do is they register that memory region as a read-only segment to the GC, right?
Correct.
But you did this completely without the runtime changes, and it's all in managed code.
Right.
So that's very cool. So let's talk about that.
Yeah. So in CLR 2.0 days when you had this thing, you would basically only be able to do strings and had to use nggen, which is somewhat limiting. So for our use case, neither of the case. We're running on .NET Core 3, and we want to be able to actually use these for all these different kinds of objects. They have lists in them, strings in them, all sorts of complicated objects. And so actually creating them is sort of interesting. The code is actually a managed NuGet package. You can add this to your
That's
application.
Great. Anybody can go
and download it, add it to their application. And essentially you think about this as like a deployment or a post-build step. You've got your application and you want to make these frozen objects.
Right.
You run your application, you point the frozen, we call this a frozen object serializer. You say, hey, I have this object and I want to just serialize this to disk as a frozen segment.
So it's like another step in your deployment.
Another step in your deployment process, you basically do this, and essentially, voila, you have these objects from non-contiguous memory on the GC heap.
Yep.
You get contiguous, essentially, objects on disk, which is really cool because you get locality benefits and all that stuff from these frozen objects.
Right.
So I can now show the sort of how we actually serialize this on disk. So here basically we're going to start with this is an object, and you can see that the object has 3 references and some long fields, and we want to start serializing this object. The thing to note is if you have this object and it has other references, we have to take care of storing the information, what we call these that are not live memory references. They're actually going to be cookies that we store on disk.
Right.
So for example, that method table pointer has to be stored and persisted in some interesting way. So what we start is we have this, and I'm going to show on the upper right corner is basically like a queue, and where there's state and action being done, whereas we enqueue and dequeue things. And this is sort of like the first step in the serializer. We go, we find these references, and we say, hey, we found we dequeue object 1, which was the root object that you basically started with, and we added object 4, which if you look is from the, have to look at from the left side, come that object 4, object 2 and object 3.
Sorry to interrupt. So that means if I have multiple objects I want to serialize, I can just make an array that points to all of them. So you start from the root object.
Right. We always start from the root object, but if you wanted to, for example, have thousands of objects, you could just make an object array.
Exactly.
Put all those, and then give the object array as the root object.
Exactly.
Correct.
Yeah.
Exactly. So here we basically have a few things going on. At the bottom, you have basically the data that's been written to disk. So object 1 has been written to disk, but you'll see that thing called reserved, and there's a dictionary there. So what we need to make sure is when you have the same reference that you've encountered, we can't actually put this, those references have referential identity, so we can't actually enqueue and write multiple objects of the same instance onto disk. So that dictionary helps with that, and also with the ability to point back at references that you have encountered as you do the object graph. So here, basically, we go and say this object, which is which its size is 64, we put that, and then we've discovered object 4, object 2, and object 3 in that order, and we've enqueued that in our queue. Note that knowing its overall size that we've encountered is actually very helpful, because then we can do all of this in one pass.
Right.
And to talk about the one pass thing, this is not actually how if the GC would do it, it would do it differently.
Right.
It would actually go do what you would do normally, mark all the objects, and then go back again on them.
Yeah.
We decided not to do that because we wanted to do this 100% outside the runtime in managed code, so we're not mutating your object.
Right. I mean, we want people's feedback on this feature, and
it's experimental.
Exactly. But if this is very helpful to a lot of people's scenarios, then we could, of course, consider putting it as a runtime feature.
In the runtime. Right. So we basically go find the next object, serialize that to disk, and again, you'll notice that the reserved region hasn't changed because we have not actually encountered another object with object references, which is the interesting part here. And then we get to the next object. Here, we have still not encountered any new object with object references, so you see we haven't reserved more space for the next set of references.
Right.
And then we find an object again with more references, and we go in and figure out, obviously write this object, but then find the reserved stuff that is going to be there coming in the future as we serialize that.
Right.
And then finally we arrive at the final object, and now there's essentially nothing else to serialize. So if you can imagine, these objects could have been anywhere in memory, but we put them together contiguous on disk, which is really helpful for
and all this is on GitHub, right? It's,
all this is on GitHub.
GitHub.com/Microsoft/frozen
objects.
Right.
It's a public repo.
Yep.
It's all in managed code.
Yeah. Feel free to go check out the code if you're, if you want to. The concrete code corresponds to the slides. Yeah.
And let us know if there's things like there are limitations. For example, we don't want to serialize things with int PTRs or things that may have file handles that are there. So there's a few things that are there, but it'd be good to get us feedback to see what to improve.
Feedback from customers on this feature. Yeah. So this is great. So when we're talking about this feature, we really want to see how can we make this faster. So you talked about serialization, right? So when you deserialize, when the process starts up, we need to load frozen objects, or just whenever registration time, you need to deserialize things into memory. That's where we really care about the perf.
Exactly.
Right.
So we did a bunch of work, as you can see, on serialization. We have dictionary lookups. We're doing all this work.
Right.
But serialization is much faster.
Right. So all we do is we have two kinds of fix-ups, right? There's the offsets that you put in for references,
right?
And then there's the method table pointer fix-ups. So of course, we're thinking like, how can we make those two go faster?
Right.
So if you can imagine, like, if we had a preferred address, we can load it
for
there.
frozen objects.
Right. Yeah. And then we don't have to write offsets. We just write the actual address.
That's one fix-up gone.
Right. And if we cannot manage to load it at the preferred address, we just go to the fix-ups as normal anyway, right? And then how do we avoid the fix-ups for method table pointers? It turned out that in the runtime, there's a way to tell the type system where to put the type info. Like you can give it a memory chunk and say, hey, just put it here. Which means if we can manage to, again, load up at the preferred address, we already knew beforehand where the method. So we were so excited when we found that out, right? But we were only happy for like a day.
Before the security people came and said that, well, because these are live pointers, the fact that you can call methods on objects, it can their security can become an issue.
Right, and there is another concern, which is the unpredictability, which means if you cannot manage to load up the preferred address, then it becomes slower.
Correct.
But personally, I think that's a lot. In the last part, we talked about large object or large pages.
Right, and unpredictability there.
Right. But I think this is a different kind of unpredictability because with large pages, you're going to have unpredictable results throughout the process. Whereas with this, it's at the time you can exactly. It's very limited in scope, right?
Yeah.
So we could tell you via entry event log and whatnot, just to tell you hey, we didn't manage to load a preferred address, so you know why that part was slower. Right?
Yeah, it's different from the large object case, large pages case. Where the idea of running your app at 10% slower performance may be significantly worse because you're running it for a long time versus a discrete phase like startup. So no, I completely agree.
So this is actually one of the other reasons why we really wanted your feedback on, right? You can let us know what you think of this unpredictability. Is it tolerable to you or not? Tell us why. We're going to put our Twitter links below, so feel free to connect with us on Twitter and tell us what you think. We really appreciate your help.
Yeah.
Right? So we've been talking about all these perf features. So clearly you care about perf tremendously, right? With that, I think diagnosability is another thing that you have to care about a lot, because when things run slower, you want to know why, right? So we're going to wrap up for this episode. Next episode, let's talk about the diagnostics work that we worked on together for Core 3.0.
Cool, sounds good.
All right, bye.
Bye.